All right, so the last portion of our notes for chapter one is over energy. Right, so I have a definition for energy here. Energy is the capacity to cause change or the ability to do work. The work part is a physics part of that definition. We don't really care. But the capacity to cause change, that is important to us, right? All the reactions that we're going to talk about in chemistry involve some energy, some way, somehow. Right? Whether it's energy absorbed or energy released by the process. Right? When one substance changes into another, there's always going to be energy involved. So we're going to talk about that. There are two major types of energy: kinetic energy and potential energy. Right? And you're fairly familiar with those things, but you usually think of them in terms of physics. Right? If I lift my book, I'm giving it potential energy because as soon as I let it go, all of that stored energy turns into motion as it falls and hits the table, right? So that's the kind of thing you're thinking about normally. Roller coaster type physics, right? What goes up must come down. But there's also other connections to those types of energy that we're going to think about too, right? Thermal energy is the movement of particles of matter. So when we talked about solids, liquids, and gases, right? Solids, liquids, and gases, they all have energy, right? But a gas is much more energetic than a solid. The gas is so energetic that the particles move freely from each other, right? They don't take on a certain volume. They fill the volume of their container, and they're allowed to move freely. Whereas at the solid end of the spectrum, the energy of those particles is small enough that they're attracted to each other and they're really stuck in place. They just vibrate, right? And then the liquid's just somewhere in between. So we're going to talk about thermal energy, not really kinetic energy specifically, right? But we're also going to talk about potential energy in terms of that energy released by chemical reactions, that potential energy that's in food that you use to do things on a daily basis, right? How you're going to grow, how you're going to move, how you're going to build things and break things down in your body. All of those require energy as well. So we have energy in bonds in chemicals, and when we break those bonds and form new ones, that energy is either going to be absorbed or released in the process. So we talk about that in depth later on. The units for energy, I believe you might have a table in your notes, but just make sure you know that physics one for energy, that unit for energy is a joule, but we're going to use calories and kilocalories a little bit more frequently, right? Because that's something that you're actually familiar with to a certain extent. This big C calorie here, right? When I use a capital C in a calorie, that's the calorie that you read on food labels all the time, right? But a big C calorie is the same thing as a kilocalorie. So if I have 1,000 of the little c calories, I have one big C calorie. I don't know who made that decision. It's actually kind of confusing, but just make sure you understand that if you see a capital C, that's a kilocalorie actually, right? The calorie, the little c calorie, is the unit that we would typically use, but a kilocalorie could also be abbreviated the same way, just with a capital letter instead of a lowercase letter. So make sure you know the difference, but otherwise we'll get to that later on more so. Reference points as far as temperature is concerned. You also have a table for this, I believe. Biggest things, boiling, freezing, those reference points. That's how Celsius was built to begin with, right? We wanted to have boiling be 100 degrees Celsius and freezing be 0. Just nice clean numbers to make everything easy for us, right? But I'm going to use those to build an equation to convert Celsius into Fahrenheit, right? So I know that I could just give you those equations, but it's actually better to see how they're derived sometimes. So the same two reference points in Fahrenheit, boiling is 212 degrees Fahrenheit, and freezing is 32 degrees Fahrenheit. Excuse me, I put a Celsius there. So you're familiar with those two reference points as well, hopefully, right? And I'm going to use those two things and these two things to figure out how to convert back and forth. So 212 minus 32 is actually 180 degrees. Right? It doesn't really matter. I don't need a symbol for this anymore. But the difference between 212 and 32 is 180. The difference between 100 and 0 is 100, which is actually part of the reason why we made it 100 and 0, because it's a power of 10 again. Right? I'm going to use this in the metric system. I don't want to do anything besides just move a decimal when I'm doing calculations, so it makes it kind of nice for us. So anyway, I take those two values, the 180, and I divide it by 100, right? And all that means is I'm going to move the decimal twice, right? These two zeros mean I'm going to move the decimal this way twice. And it gives me this decimal value of 1.8. Sometimes it's written as a fraction, 9 over 5, because those two things would be equivalent. Excuse me, I kind of goofed up that 5 there. So you might see that in an equation at some point or another. But essentially what I'm going to have to do is I'm going to have to take 1.8 times my degrees Celsius, right? If that degree Celsius value was 0, 1.8 times 0 is 0. So then I have to add 32 to get to my other reference point in Fahrenheit. So 1.8 times degrees Celsius plus a 32 is going to give me my degrees Fahrenheit. And conversely, if you do a little bit of algebra, I can take that degree Fahrenheit and subtract 32 from it, and then divide whatever my answer is there by 1.8, and that's going to give me my degrees Celsius. So I need to know how to convert from one thing to the other, and those are my equations for it. And I don't try to teach those to be memorized, because if you actually know 212 and 32 and 100 and 0, you could figure out what the conversion was yourself easily, very easily. So yeah, you're going to put those on your cheat sheet for your tests so that when you do a temperature conversion you can get it done. But otherwise, that's something that you could come up with on your own pretty easily. Right? So I just gave you two conversions. The last conversion actually has to do with the fact that Kelvin exists for one purpose and one purpose only. Because there is an absolute zero, because it is possible to make particles slow down so much that they would stop moving. That's still theoretical. We can't actually reach absolute zero. We've never found the actual zero. We can just extrapolate data from what we have approached. And it gives us this idea that it's somewhere around negative 273 Celsius, right? And that's actually not very precise. 273, right, 0.14 is a more precise number, but we don't really care for our purposes. Right? We don't need to have too many sig figs with our temperatures most of the time. So what we're going to use is that 273. And essentially, if 0 is negative 273, then if I take my degrees Celsius and I add 273 to it, that would give me my degrees Kelvin. Excuse me, it's just Kelvin. There are no degrees for Kelvin. But if I add 273 to Celsius, it would give me this Kelvin value that could never, ever, ever be negative. That's the whole point, right? Because if I have to put a temperature value into an equation, I can't have a negative number messing with the rest of my answer. So Kelvin exists for one purpose, to make sure there is never a negative number. And since negative 273 Celsius is absolute zero, if I add 273 to Celsius, I get Kelvin. Obviously, I can subtract 273 from Kelvin to get Celsius. It kind of depends on the situation. 273 is not actually a very big number. So once you start talking about the surface temperature of the sun at 10 million degrees Celsius, it's also 10 million degrees Kelvin, because 273 becomes very, very negligible at that point. So It depends on what kind of science you're in. Sometimes it matters if it's Celsius or Kelvin. Sometimes it actually doesn't. But just be able to convert back and forth. So you need that equation. You also need those two equations we derived on this slide. So make sure you put those in your notes somewhere, but you could come up with those on your own as well. But you need to be able to use those, obviously, to convert temperatures. So at this point, I would suggest that you go ahead and pause the video, because I believe you could use an equation, plug in one number, try and come up with another one. So you should go ahead and practice that, and then restart the video, and then you can see if you did it right. So I'll go through it, I'll show you how to do it, I'll give you the answers. But if you already think you kind of know how to do it, just go ahead and skip ahead to the end of the video, see the answer. And if your answers are right, then you're great. So again, I'd pause now, go ahead and check it later. But otherwise, I'm going to do these conversions at 23 degrees Celsius into Fahrenheit. So again, I'd use that equation where I'd take 1.8 times the 23, and then I would add 32, and that should give me my degrees Fahrenheit. So gotta grab a calculator here real quick because I don't know what that is in my head. But if I took 23 times 1.8, I'd get 41.4. Now, one thing that you guys should recognize here is if I was going to use sig figs, if I was going to be rounding appropriately, I can only have 2 sig figs in this answer right now. And usually you don't round something until you're done, but I'm actually going to use 2 different rules for rounding in the same problem. Since I'm going to add a 32 to this, and this 2 is in the ones place, I'm only going to end up with precision to the ones place anyway. So it really doesn't matter in this context. It also depends if you consider that 32 an exact number or not, because it is defined to be exactly 32 degrees Fahrenheit that's freezing. So it's kind of iffy, but my 1.8, my 23, those also only have 2 sig figs. So I should probably have 2 sig figs in my answer. Usually if it's a temperature, I'll tell you what to round it to, because otherwise we'll get really confused. But anyway, since it's a 23, I do need to round this here, so it's actually a 41 plus a 32 is a 73 degrees Fahrenheit. Right? So then the next one, 105 degrees Fahrenheit into Celsius. Right? If I start out by subtracting 32, 105 minus 32, that's actually going to give me a value of, let me check real quick, I don't want to do it wrong. So it's a 73, and I'm going to divide that value by 1.8 because that's what my equation tells me to do. That I definitely can't do in my head. So check that real quick, and I get an answer of 40.5, and that 5 is repeating actually, right? Again, I do have to round appropriately. Because the 73 has 2 sig figs, I'd probably keep it with 2 sig figs, so this should be rounded to 41 degrees Celsius. But again, if you're having to round with temperature conversions, I'll usually tell you where to round. Okay, so your final conversion down there has 2 steps. I need to change it from Fahrenheit to Celsius and then change it into Kelvin. So I'm going to use the same equation as the last one. I'm going to take 0 minus 32, which is just a negative 32. But then I'm going to divide by 1.8. Don't know what that is. So 32 divided by 1.8. It's going to be 17.7 repeating. And again, that's degrees Celsius already. I could round this. Obviously, I'd only have 2 sig figs in this context from what I was given. I was actually given an exact number 0, which is kind of hard to decide if that has any significance or not. But for our purposes, we'll just go ahead and let this have 2 sig figs still. Let it be rounded to the ones place. So that's going to be an 18 degrees Celsius. But then I need to add 273 because I want Kelvin. So again, 18 plus 273, just so I don't make a mistake, is 291. 291. I actually lose the degree symbol. I just write Kelvin. That would be my answer. So again, if you just skipped ahead and you have these three answers, you're probably good. Otherwise, your homework for today is really just finish your practice problems. Right? When I come back to class tomorrow, we're probably going to have another quiz to kind of culminate this chapter. But otherwise, should be good to go.